Everything is ready, I think.
Screen visible to everyone?
Okay, so let's move on to the last talk of today, which is Daniel Berwick-Evans, who will speak about how do field theories detect torsion in topological modular forms. Please.
Thank you for having me. It's great to be part of this. I think these sorts of events nowadays are really great to be able to see colleagues and discuss these sorts of things. So this talk is going to be about something a bit different than some of the others, perhaps a little different flavor. So let me just start by explaining kind of the context for where this work sits. So there's this conjecture from started in the 80s, ideas due to Witten, and then continued with Siegel, and then continued with Stoltz and Teichner. And the conjecture relates a certain object from physics with a certain object in homotopy theory. So the object from physics is some category of field theories, which I'll say a little bit about briefly right now, but discuss in more detail later. And here M is going to be a smooth manifold. And so there's a category of field theories that gets attached to M, and very roughly it's something like 2D supersymmetric field theories over M. Again, I'll have more to say about that in a bit. And the essence of the conjecture is that there's a cocycle map that lands in topological modular forms of M. And I'll also have more to say about TMF in a second. But first, let me just give you an analogy, how to think about what this is good for, why you might be interested. So the analogy is that in K-theory, there's this cocycle map that goes from vector bundles over M, and lands in the K-theory of M. And this relationship between vector bundles and K-theory is the starting point for lots of great stories in math. I mean, if you make this equivariant, then you get these connections with representation theory. You have various connections with analysis via C-star algebras, Fred-Hellman bridges, et cetera. So sort of the starting point for many beautiful stories in math is this cocycle map for K-theory. And the hope is that having a cocycle map for this more sophisticated object, topological modular forms, will lead to similar interesting stories. So just to kind of say a little bit more about these field theories, this supersymmetry here has to do with this number out in front. There's a two-dimensional field theory with one supersymmetry, which is sort of like one nilpotent direction in the sense of algebraic geometry, and that kind of feature later on as well. But at least to start, you should just think about this as a 2D field theory, some functor from a Bordism category of two manifolds to vector spaces, and that's supposed to be one of the underlying objects. All right, so immediately once this conjecture is lodged in your mind, there's a mystery. And the mystery comes from what we know about TMF. TMF has a lot of torsion. This torsion is related to the homotopy groups of spheres on the one hand, various other interesting number theoretic objects on the other. And it's not at all clear on the field theory side where this torsion might come from. So this mystery is where is the torsion in field theories? And so my goal today is to both give you a sense of the two sides of this conjecture and also a partial answer to this mystery. And the partialness of the answer will come from approximating both sides of the conjecture by simpler objects and showing that those simplifications already detect some torsion. So roughly, the rough plan is to approximate to 1 QFT of M, and also approximate TMF of M. And then with those approximations, we can write down cocycle map. I want that to be in red. And these approximations are going to be a little less fancy than the full-fledged objects. So hopefully that will also make the conjecture itself a little more intelligible, a little more kind of down to earth as we go. And just for those that may have heard some of these words before, the approximation on the field theory side is going to be something like a one extended version. So in the sense of the Coe-Borzum hypothesis, and the approximation on the TMF side is going to be something like a height less than or equal to one approximation in the sense of chromatic homotopy theory. So again, if those words don't mean much, we'll get to sort of what the essence is later, but that's at least the plan. So the danger in these sorts of talks always is that both sides of this conjecture are fairly fancy, and they might be things that you haven't thought about much before. So I'll do my best to make things as clear as possible, but please interrupt me if something is not clear to you. It's very likely that it's also probably not clear to others. And I have the sense that the backgrounds amongst the audience today are quite varied, so I don't want to run away and just end up shutting into the vacuum of the internet by myself. So please interrupt me if you have questions. Okay, so so far, are there any questions just about the motivation?
Maybe just one little question. So I'm always confused about all these manifolds that are in the Schultz-Teichner program. How should I think of M? Should I think of it as like a target space or a family over M?
Right. Yeah, so there's sort of two alternative points of view on this depending on how you want to think about this. So you should, at the very minimum, be thinking of M as the thing whose cohomology we are trying to evaluate. So on the one hand, you might think about a vector bundle as being a family of vector spaces parametrized by M. That's certainly one way. And field theory should be of a similar flavor, that there's like a family of field theories parametrized by M. You might also think of a vector bundle as a gadget that assigns to points in M a vector space into a path in M if I have a connection, a linear map. And in this case, then M is like the target space for sort of the thing out of which you build a path category, whose representations you take, and that's related to vector bundles. So similarly, field theories you can think of as mapping two-dimensional Bordisms into M, and then a representation of that category would give a field theory. They're roughly equivalent points of view. Sort of the difference between the vector bundle cases that I mentioned is the date of a connection. That's contractible data. So they're roughly equivalent up to that sort of caveat, or at least that's the expectation in the two-dimensional case as well. Any other questions? Okay, so let me start by just talking a little bit about topological modular forms. So this is this very beautiful object that came out of the work of Hopkins and Gorse and Miller in the 90s, and then has recently been taken up by Jacob Lurie, or I don't know how recent it is now. The survey is old, but the papers are coming out very rapidly now. And so there's this beautiful connection between elliptic curves and spectra. I want to just give, in varying degrees of sophistication, how you might think about TMF. So first, we ought to think about what modular forms are again. So a modular form, these are going to be a ring, or a graded ring, and it's given by, say, functions, holomorphic functions on the upper half plane in the complex numbers with a property, a modularity property, about how they transform under fractional linear transformations. Here tau is a point in the half plane, k is an integer, usually called the weight, and then a, b, c, d is something in SL2Z. Okay, so that's just up to, there's some issue about what happens at I infinity that I'm just going to ignore for now, but this is just one way at least to begin thinking about this, these classical modular forms. So they've been studied in all sorts of different areas, have deep impact in number theory, amongst other places. And that's at least one starting point that you might think about topological modular forms as an enhancement of modular forms. So TMF has, well, first of all, it's a cohomology theory. Whose coefficients refine just ordinary modular forms. So by that I mean that there's a map that's a rational isomorphism, and the kernel and co-kernel of the map are a bunch of interesting torsion. And the torsion is really what makes TMF interesting. Again, this torsion is related to homotopy groups of spheres, various other arithmetic problems, Borcher's congruences. I could name various other buzzwords, but the point is there's a lot of algebraic interest that comes out of that torsion. And so this refinement has a lot of content to it that's maybe kind of being pushed in the background by just saying this is a rational isomorphism. Okay, so that's at least the first way to think about TMF, is it's an enhancement of modular forms, hence topological modular forms. Okay, but let's kind of get into a bit more detail. How is TMF constructed? So TMF is constructed as a homotopy limit over these things called elliptic spectra. So the only thing I'll say about elliptic spectra is that they represent certain cohomology theories that are determined by their theory of Chern classes. So elliptic spectra represent cohomology theories that are determined by their theory of Chern classes. And just in a bit more detail, what I mean by that is that, say, in ordinary cohomology, we know that if you have line bundles L and L prime, complex line bundles, that the first Chern class of the tensor product of those line bundles is the sum of the Chern classes. This is one of the key properties of Chern classes that allows you to do all sorts of stuff. Now, in elliptic homology, the situation is a little bit more interesting. That this theory of Chern classes, well, it has the first same two terms. You get just the sum of the Chern classes, but then there's higher stuff. And this fits together to give a power series in two variables. Those variables are the Chern classes of the respective line bundles. And that power series itself is a formal group law. And specifically, it's a formal group law associated to an elliptic curve. If you haven't seen formal group laws much before, very roughly, you can think about this as starting with the multiplication on an elliptic curve. That's a one-dimensional group object. And you can Taylor expand that multiplication near the identity. That gives you some power series in two variables. That's your formal group law. So very roughly, this is given by Taylor expansion of the multiplication on your elliptic curve. Okay, so that's going to, again, give some power series, and by some, it's kind of a long and beautiful story that unfortunately I don't have time to tell, but that formal group law determines a cohomology theory. Out of that, you can build a spectrum, and then TMF is going to be some homotopy limit over all of those spectra. So kind of the takeaway from this is that elliptic cohomology has kind of sitting inside of it all this data about elliptic curves, but also something about these different homotopy compatibilities, because it's a homotopy limit, not just a limit. And those homotopy compatibilities are where all this subtle torsion comes from. Okay, any questions so far? This is like the briefest introduction to TMF that I could think of. But I'm probably not doing it much service if you know TMF very well, and I'm not sure if you haven't seen TMF how helpful this is, but please ask questions. Okay, so the next thing I want to do is, with this description of TMF as a homotopy limit, we can write down approximations to TMF by mapping out of that homotopy limit. And mapping out of a homotopy limit is easy by using the universal property. So this is how we're going to approximate TMF. Okay, so let's start up here. We have TMF. Again, I'm only really going to treat it as this thing that has the universal property of the homotopy limit. And I'm going to tell you about my favorite elliptic curves, and that'll give me maps out of TMF. So we get maps out from families of elliptic curves. And one classic family of elliptic curves is the Tate curve, or maybe the formal neighborhood of the Tate curve. And this is over this formal punctured disk. And what you get from that evaluation is real K theory with power series in Q. So this is going to be specified, a class in here is specified by an infinite sequence of vector bundles over some space, one for each power of Q. That's one map out of TMF. Another map comes from thinking about elliptic curves over C. And this gives us back this ordinary cohomology with coefficients in modular forms, just the good old modular forms, like that. And now another thing you can do is take the family of elliptic curves given by the Tate curve and take its complex points, and that's going to give some compatibility between these two maps. So that gives me maps down to ordinary cohomology with coefficients, power series in Q with now complex coefficients. And now these two latter maps actually have simpler descriptions in terms of things we know about K theory and ordinary cohomology. This first map here is just given by the Chern character in each power of Q. And this map over here is induced by a map on coefficients, which is usually called Q expansion. But there's basically a Fourier transform map on modular forms that lands in power series in Q, and that map on coefficients gives this map of ordinary cohomology theories. Okay, so far I've just written as though this were a limit diagram rather than a homotopy limit diagram. The important thing now is that there's actually more data going on, which is there's a homotopy between the compositions of maps from TMF down to ordinary cohomology with coefficients, power series in Q with C coefficients.
Sorry.
And the thing I want to think of, oh, yeah, sorry.
Sorry, can I just ask a quick question? So you are emphasizing
Please.
the fact that TMF is homotopy limit and universal properties giving you these maps, right? So
Yes.
I'm a bit confused, like how a map out of homotopy limit.
Oh, these are part of the limit diagram, so it's a cone over the limit diagram. So
oh,
I
see, and you are putting in the terms of the diagram in there. I see. Okay, sorry.
Yeah, sorry. Maybe yeah, you're right though. I probably using the universal property that it maps into its diagram. Sorry, yeah, that was probably a confusing way of phrasing it. You're absolutely right. Thank you. Yeah, but these are parts of the limit diagram, so we get maps. Thanks. Any other questions?
What was HMF?
Oh, so this is okay. Both of these guys down here are ordinary cohomology theories. So this is ordinary cohomology with coefficients in modular forms.
Okay.
So MF was this ring that we talked about up here, where you have holomorphic functions on the half plane with transformation properties. And this K over here gives a grading. And that's going to be the graded ring that we take. Well, you make it a supercommutative ring by putting some zeros and odd degrees, and then I can see the ring down here. And similarly over here, this is just ordinary cohomology with coefficients, power series, and Q. Okay, so what I want to do next is take the homotopy pullback, which I'll just define as being some mashup of KO and modular forms. And this map here is the approximation that I want to consider. Maybe I'll put that in a different color. Okay, so in particular, a map into KOMF will be something with power series in Q, something from ordinary cohomology with coefficients and modular forms, together with a homotopy between the image of those classes down below. So that homotopic coherence will turn out to be very important going forward. In particular, if you think about the coefficients for KOMF, So the coefficients of KOMF. In even degrees, they're almost, up to some 2 torsion, they're almost just integral modular forms. Even degrees are, so often integral modular forms are written like this. These are modular forms whose Q expansion has integral coefficients. In any case, it's just a refinement of the ring of modular forms, if you like there. In odd degrees, there are these kind of huge rings that accommodate torsion, or huge abelian groups that accommodate torsion. So the reason for that is that if you just think about it in coefficients, the maps in this homotopy pullback square that I mentioned, they don't surject onto the lower right corner. So when you look at the Meyer-Vietoris sequence, long exact sequence associated with this, you end up with some funny quotients. It's very roughly going to be like power series with coefficients in C mod power series with coefficients in Z. So you get all of these C mod Z's, and you can certainly map torsion groups into C mod Z. Okay, so any questions on this approximation first before I go forward? Maybe one thing to say for the chromatically minded in the audience, if you're out there, is that this is being built out of things of height 1 and height 0. So ordinary cohomology theories, these are all rational. So these are just height 0 objects. K theory is height 1, and this is some kind of mishmash of the height 1 and height 0 parts of TMF in that way. Okay, so the next thing I want to do is talk about maps into KLMF, and specifically I want to start with this thing called M string. There's the string orientation of TMF, which is similar to the spin orientation of real K theory. And M string is basically given by spin manifolds with P1 over 2, so fractional Pontryagin eigenclass equal to 0. So that is to say that a manifold is string if it's spin, and then some additional characteristic class vanishes. And there's this string orientation constructed by Ando, Hopkins, Strickland, and Resk of TMF that is sort of analogous to the spin orientation in K theory. And you can consider now the composition from M string down to KLMF. And I just want to spell out in detail what that entails. So the map M string to TMF gives data. So the first piece of data is a map that is from M string to KO, power series in Q. And this factors through a spin orientation of KO. This is a spin orientation, or KO with power series in Q. This was written down by Witten in his seminal paper on the subject. And he calls this orientation the Dirac operator on a loop space. So this is Witten's Dirac operator on loop space. Now I should be clear that Witten doesn't actually give you a Dirac operator on the free loop space, but nevertheless, this is sort of supposed to be related to that way of thinking. Okay, so the other piece of data you have is a map from M string to ordinary cohomology with coefficients and modular forms. And this factors through the same type, string manifolds where all the characteristic class conditions you want to make are only given rationally. So I'll write that as M string Q. So factors like that. So rationally, a spin manifold is just going to be an oriented manifold, and then the string condition is just P1 vanishing in a rational cohomology. And by playing around with the Riemann-Roch theorem for a little while, you'll learn that this orientation is just given by the usual orientation in ordinary cohomology modified by a characteristic class that's usually called the Witten class. So by Riemann-Roch theorem, this is the usual MSO orientation of ordinary cohomology, and then modified by a characteristic class, which is usually called the Witten class. So in formulas, if you want to push forward along a family of rational string manifolds, this is just given by the usual push forward, like integration of differential forms, push forward, wedge with a certain characteristic class. Okay, let me just pause for a minute. If the things in the right-hand column are not familiar objects to you, all I'm getting at here is that these orientations of these cohomology theories are things that we know well. They're not kind of mysterious in any way at all. They're built out of objects that have been well known for at least 40 or 50 years. Things like Dirac operators, things like differential forms, etc. So in spite of the fact that the string orientation of TMF is something very complicated and not very well understood, the string orientation of these pieces of TMF are well understood. And furthermore, together with some homotopy compatibility, this makes the string orientation of KOMF something well understood as well. So the last piece of data of this orientation is a homotopy compatibility. Between a pair of maps from M string to ordinary cohomology of power series in Q. And this compatibility is also something well understood. It will depend on the trivialization of P1. So this is determined by a trivialization of P1. And this is just a rational trivialization. So explicitly, when you're doing these calculations, you're going to be asking for a degree 3 cochain, D of which is P1. So again, the point is, if the right-hand column is a bunch of words that are unfamiliar, this orientation I'm talking about of KOMF is something that's fairly classical, and you can just do a lot of calculations using kind of like 1970s and 80s level technology. Whereas understanding the string orientation of TMF requires more sophisticated things. Okay, so this string orientation of KOMF is going to be useful down the road. I'll talk about it in a minute, but are there any questions, first of all, on just the setup? Trying to kind of keep TMF itself in the background, but emphasize that these pieces of it can be well understood.
Sorry, just a very stupid question, if I may. This power series variable at KO is a formal thing, right? It's just, I can think of it as an infinite product.
Correct, yeah. I mean, yeah, certainly if the space is compact, that's true. I'd have to think a little bit about what to do. I mean, there's something, yeah, I think certainly the first approximation, you're right. If the space I'm trying to put in is a finite CW complex, I don't think there's any issue with what you just said. If it's an infinite CW complex, I might have to think a little bit about how that colimit works. But yeah, that's correct.
All right, thank you.
Yeah. Okay. So the next thing is, great, we have this approximation, but when you have an approximation, the question is how good is it? And since the goal here was to get torsion, we need to know that KOMF actually sees some torsion. So let me now explain to you some of the torsion that KOMF can see. So here's some facts about KOMF and TMF torsion. And these are sort of repackaged results of Lee Bunke and Nico Naumann. They have a paper about secondary invariance of the Witten genus. And if you think in this way about their invariance, you'll see that they're actually telling you about this map from, for example, pi star of TMF to pi star of KOMF. And what they tell you is that this map on coefficients, this injects 3 torsion in certain degrees. So this injects 3 torsion in degrees 4k minus 1. So the point is that, at least for some torsion in some degrees, KOMF is actually a pretty good approximation. The other thing that they show, which is kind of nice, is that the this generator for the Z mod 24, which is related to this third stable homotopy group of spheres in pi3 of TMF, this also injects into pi3 of KOMF. So in a sense, the first kind of torsion invariant in the coefficients of TMF that's not present in KO is this thing nu in degree 3, and it can be detected by KOMF. That's another nice thing. In fact, if you, what they really show is that if you look at the composite from M string to TMF to KOMF, if you look at where the 3 sphere goes here, it's going to go, well, first to the generator of the Z mod 24 in degree 3, and then this includes into some big group. So in fact, you can show that this works by considering what happens with the string orientation. Okay, any questions on that? So I'm about to switch gears to field theories. Let me just recap what's happened so far. We wanted to study TMF. TMF is hard. We want to study the string orientation of TMF as well. That's also hard. We made this approximation using this homotopy pullback square by a cohomology theory that can be studied using more standard geometric techniques, where the string orientation is determined by more classical orientations, namely the spin orientation of KO, ordinary orientations of cohomology, and various compatibilities between those. And furthermore, that orientation actually has some interesting torsion invariants in it related to, for example, pi3 of TMF. All right, so the next thing I want to talk about are the other side of this conjecture, these supersymmetric field theories.
Sorry, just another question. I mean, maybe this is boring, but if you invert now 2 and if you invert 2 and 3, I mean, TMF then sort of becomes a bit simpler. Is this map also an isomorphism or something close to it? I don't know.
I don't think so. So, okay, so one way of thinking about this is in relation to the moduli problems associated to them. So elliptic homology with 6 inverted is you're looking at the moduli of elliptic curves with 6 inverted, and you're taking global sections of some structure sheaf. Up here, this is kind of much weirder in terms of that picture, because what you're doing is you're looking at a formal neighborhood of the Tate curve, and you're looking at the rational locus everywhere else, and you're gluing those together. So, I mean, kind of loosely they're related, but I don't think there's a map actually in either direction. And somehow this integral data at infinity is not going to be present when you invert 6, and then this data with 6 inverted, but not rational data, and the other locus is not going to be present here. So I think I agree with you that there's sort of some resonance between those 2 points of view, that you're making a moduli problem easier, but I think they're actually in reality different.
All right, thank you.
Sure. Any other questions? Okay, so now we're going to talk a little bit about field theories. So supersymmetric field theories. And I'm going to at least try to sketch for you how the definition of this goes. I should give the caveat that somehow the complete definitions are still very much in flux. The stuff I'll tell you about today relies on a specific definition that is rock solid, but somehow has some pieces that I know are not going to, that need to be refined for the full conjecture. And I'll try and say some things about that later on. So the full relation to TMF. So the definition I have in mind, and again, here as above, M is going to be a smooth manifold. I'm going to study this category of quantum field theories over M, which will be defined as symmetric monoidal functors. So this fun with the tensor is symmetric monoidal functors from a certain Bordisan category. That's an M, to a category of vector spaces. And then there's one additional thing that if people press me on it, I can talk about later, but there's a technical condition that's sort of analogous in K-theory to ellipticity of elliptic operators. So that's an important feature in the index theorem and K-theory, and there's a modification of Stilson-Teichner's definition that requires this to get some of the things to work that I'm going to mention later. Okay, but let me just zoom in a little bit and tell you a bit more about how to think about this Borzon category. So the morphisms of 2-1 board of M are certain supermanifolds with a map to M. And I'll say more about that in a second, but let me just write that first. So are certain supermanifolds sigma with a map from sigma to M. Let me actually give this some decorations. So let's call it like sigma tilde. So supermanifolds are sort of a technical field. Very roughly, they're like nilpotent thickenings of ordinary manifolds where the nilpotent thickening has some grading on it. So if you thought about non-reduced schemes, it sort of falls into that area of geometry. But let me say what this looks like in terms of more standard, just 2D geometry. So roughly, this is going to be a 2D surface sigma with a flat metric. Like a line bundle over it that's going to be regarded as odd in the superworld. And a map from the total space of that line bundle to M. So the important thing here is that we're looking at 2D surfaces. This flatness condition is actually kind of a restrictive one, right? There aren't that many 2D surfaces with the flat metric. By the Gaspinet theorem, you know that at least when you're looking at closed ones, that's just going to be your torus. Oh, these are also oriented. Everything will be oriented. So it's just the torus, no Klein bottle. So on the one hand, these theories are going to be simpler than maybe the more understood 2D topological field theories, because the Borzon categories just have these flat things in it. On the other hand, the dependence on that moduli of flat structures will be here. So that's going to add some complexity beyond the usual 2D topological story. So it's sort of better and worse than that more common story that you might know about with 2D TFTs. Okay, so the pictures to keep in mind are that there aren't going to be any pairs of pants. There's just like cylinders and tori and unions of those. I mean, you can write your cylinders going in different ways, but there aren't going to be anything that don't, where you can't have a flat metric and geodesically embedded boundary. Okay, so that's at least very briefly how to think about these field theories. It's a functor from Borzon category. This Borzon category has some decorations. Those decorations restrict the Bordisms considerably that we have.
So the flatness is just a simplification assumption, right? Or is there another motivation for it?
There's a reason from physics that okay, well, let's see. There are two answers to that question. It's not a simplification. It's actually probably essential to make the conjecture true. One reason is that, elliptical homology, you just see tori. You don't see functions on homogeneous surfaces. And so you don't expect those homogeneous surfaces to play a role. And one way to force that to happen is to require this flat metric. That's a math reason, kind of an a posteriori reason connected to elliptical homology. A physics reason is that when you're studying quantum field theory and physics, things start off living on flat space. And then it's only if they have additional symmetry that you can put them on curved space. Witten's famous A and B twists are of this flavor, where you do something to get extra symmetry to emerge, and then you can put things on curved surfaces. So that's sort of a standard thing that happens in physics, that you always start life in flat space. And for these theories, at least the moduli of them, you don't want that additional symmetry generically. You might have points in the moduli space of theories that have extra symmetry, but you want to somehow allow for paths between them that don't have symmetry. Any other questions?
Sorry, did you just describe morphisms in this category or objects?
Yeah, this is right. This is MOR was morphism. Maybe I should have actually written morphism. Yeah.
And what are the objects?
They're going to be the boundaries.
Oh, I see. Okay.
So yeah.
Thanks.
Yeah, right. Sorry. yeah, thinking about borders and categories for a while, maybe perhaps the morphisms are usually where like the meat is, and then right the boundaries tell you about the object. So yeah, you know, this guy here is a bourdism from the empty set to the empty set. This guy is a bourdism from the circle to the circle. This guy's from two circles to the empty set, or empty to two circles, depending on which way you want to read.
You're
Additional
saying,
questions? Cool.
so you have a complex
Yeah.
line bundle. Is that like what a supermanifold is, or is that extra data? Or
right, so the data of a supermanifold just in general is an ordinary manifold together with a vector bundle over that manifold. And then the maps between supermanifolds end up being more complicated than just maps of manifolds with vector bundles. That's what makes that category more interesting. But in terms of objects, the category of supermanifolds, at least you can always, this is a theorem of Marjorie Batchelor, that you can always consider the objects as just being a manifold with a vector bundle over that manifold. And you think about that vector bundle as being sort of like the nilpotent directions in which you're allowed to deform your ordinary manifold. That's the sense in which it's a nilpotent thickening. Other questions? Okay, so the next goal is going to be to very much an analogy with what we did with TMF, that you want to start with this complicated object TMF and map out of it to simpler things. So here we're going to start with this complicated object field theories, two one-dimensional field theories. We're going to map out of field theories in various ways. And the way we'll do it is by restricting to subcategories of the Borzon category. If you have a subcategory, the Borzon category, you can restrict a functor out of the Borzon category to that subcategory. That gives a map out of field theories. So I'm going to go through that in more detail now. So maps out of field theories. And this is going to be by restriction to subcategories. In pictures, a field theory is going to assign to each of these bourdisms some kind of linear algebraic data. It'll be like a linear map. If you have a bourdism from a circle to a circle, it's a linear map from the Hilbert space associated with one circle to the other Hilbert space associated with the other circle. And this restriction to subcategories is just going to restrict the pictures that you're allowed to draw for which you're going to ask for data, right? So starting with 2, 1 QFT up here, the first restriction I want to consider is to annuli. And I'm just going to keep the super in parentheses. So another way of thinking about it is that this is the path category of the free loop space. And that's going to land me down in some representations of that path category. So the path category of the loop space of M. Okay, so if you are accustomed to thinking about maybe vector bundles with connection as representations of a path category, so it assigns to every point in M a vector space, to every path in M a linear map. This is the same type of idea, but just now it's over the free loop space. And there's some super junk in the background that I'm just going to kind of ignore for now. Brush under the rug. Another restriction you can make is to super tori, or to tori. So this is just like the double loop space of M, but again with some decorations. So you're going to end up with functions on the super double loop space. Okay, so just in pictures up here, we're looking at cylinders mapping into M. Over here, we're looking at tori mapping into M. And there's a compatibility between these two, which is you can think of if I have a torus with a marked circle, you can either read that as an annulus, where the source and target circle happen to match, or as a torus. This is going to give a compatibility between these two restrictions. So this will be functions on tori in M with a marked circle. And the map here is going to be basically a trace map. Or if I have this representation of the path category, if I have loops in that path category, that's going to give me an endomorphism, and I can trace that endomorphism. That'll give a map down there. This map here is basically just a restriction. Or if you prefer, there's the map that forgets the circle in a torus that gives a map on moduli spaces one way, you get a map on functions the other. Okay, so this is supposed to be drawn to remind you of a diagram we saw earlier. Just scroll up to it, is this one involving TMF, where you mapped out of it in different ways, and there was a compatibility, and that gave you a map into some pullback. Well, the same thing's going to happen here. So the first proposition identifies these restrictions with cocycles for certain cohomology theories. So there are cocycle maps. The first one is if you have these representations of annuli, there's a map from these things to KO with power series in Q of M. I'll put the M before the Q. And the second is that if you're taking functions on this super double loop space, there's a map to the ordinary cohomology with coefficients and modular forms. So functions on the super double loop space. This has a map to ordinary cohomology of M with coefficients and modular forms. Okay, so I probably don't have time to tell you very much about the proofs, but let me just kind of mention their flavor at least. This one here is basically a computation where you need to compute functions on some supermoduli space. I mean, it's not without its technical difficulties, but it really just boils down to computing. This one up here, for one, is more of an index bundle construction in the sense of index theory. And that's where this technical assumption I mentioned up above about some ellipticity of families shows up. So in any case, the point that I'm making here is that these are proofs that kind of follow sort of standard methods, but applied in a slightly new way here, where you need to take now the index bundle, not of say a family of Dirac operators, but a family of field theories that involves some massaging of the data. And these functions on the double loop space, because of this kind of super geometric aspect, are both more rich and more complicated. And computing that is sort of the heart of part 2 here. And then I think you can begin to see the storm clouds gather. There's going to be a map from the compatibility between these two things to KOMF. So the theorem is that the compatibility between 1 and 2 determines a map from 2 1 QFT of M to KOMF of M. And so this is what will allow us to start to try to pick off torsion variants of field theories. So this allows us to start to calculate torsion variants of field theories. So I'll say a bit more about that in just a second, but for now, I just want to give the picture again that you're starting with this category of field theories. It's very complicated, hard to analyze, but it has these nice subcategories, for example, of annuli that glue together, or just tori as boards from the empty set to itself. You can restrict those subcategories, and what you get is something that's actually calculable. I mean, you can just calculate what that restriction is, and you find these relationships with representations of annuli in M and functions on double loop spaces of M, things like that, that then you can calculate using geometric techniques. But furthermore, the compatibility between these restrictions is what's giving you this map to KOMF, where maybe torsion starts to show up. Any questions on that? So as one more just remark here, is that this theorem extends results of Stoltz and Teichner. Where they showed that if you look in even degrees over a point, that there's a map to integral modular forms. And so this is both extending away from even degrees. Those odd degrees are where that torsion shows up. So it's extending to that case. And it's also extending the families. So replaces point by any manifold M. And even with arbitrary degree. So some of the ideas that go into the proof are very similar to theirs. But again, this extension requires treating the families in an appropriate way. Okay, like the M parameter is really the technical part.
Just a very naive question. I mean, this compatibility doesn't require anything like some version of index theorem or something like that?
It does, yeah. I mean, right. So, right, we can certainly talk about this in more detail after, but let me just say kind of roughly what goes on is that if you have a family of operators and you have its Chern character, you need like a differential form value character. So this is like Bismuth's index theorem, Bismuth family index theorem. There's a version of that that's sort of forced by the definitions of field theories here to take place. And then you have compatibility between differential form value Chern characters of some index and a differential form with coefficients of modular forms, and various homotopy compatibilities give you this map. So there's, yes, this type of stuff is under the hood. I don't know, actually I haven't thought about if it really relies on the index theorem itself, but certainly the techniques and the ideas and the constructions of index theory show up prominently in the proof. And I would guess that because of that, in one way or another, it depends on the index theorem. But I don't know for sure. I have to think about that some more.
Thank you.
Yeah.
I somehow missed what the degree of a quantum field theory is.
Right, it's because I didn't explain it. Yeah, so in the background here, there's some notion of degree. Very roughly speaking, it's that rather than considering values in vector spaces, you're considering values over some module for an algebra, and that algebra is indexed by an integer n. In K-theory, this would be the Clifford algebras, Clifford n, that are giving you this indexing. Here it's some kind of fancier version of the Clifford algebra, some infinite dimensional version of them. Yeah, they're sometimes called free fermion algebras, if that means anything. But yeah, it's like a infinite rank version of Clifford algebras. More questions? Okay, so now I just want to mention kind of from this main result about this map from an approximation of field theories to an approximation of TMF, what can we do? And the first thing I want to explain is that to start to get things like the string orientation to fit in, you need to sort of modify your definition of field theory a little bit so that you can actually construct things based upon the data given in these propositions. So that is to say, you want to consider the subcategory of bordisms that's generated by these annuline tori. So let 2, 1, this is going to be lowercase bord of M, denote the subcategory of the capital version generated by tori and annuli. So roughly, you should think of this as like the one extended version. So this is the one extended bordism category. And this is kind of in contrast to 2 extended, which would have manifolds with corners and things like that. And then just define a version of little QFT as representations of this subcategory. Oops. All right, so on this subcategory, you can now start to use index theoretic constructions to build field theories. So the next theorem is that there's a refinement of the string orientation of KOMF in terms of these field theories. So there is a map that goes from string manifolds over M, and it maps to 2,1 QFT of M, refining this map from M string to KOMF. So refining in the sense that there's a composition now, this cocycle map from 2,1 QFT of M down to KOMF of M, and the composition is going to give you the string orientation. So as a core, okay, so is that for small parse? Okay, that we're using theorem up above, up there, map from 2,1 QFT to KOMF. We know that KOMF had the string orientation, and you're saying that, okay, the string orientation actually can be computed at the level of cocycles under this correspondence. So now we can start to use these calculations that we already knew about from Bunke and Naumann, telling us where to look for torsion. So here's a corollary, is that the image of S3, so that's going to be a string manifold over point in 2,1 QFT of point. This refines this generator nu. I'll write it as k times nu in pi3 TMF, which sits inside of pi3 of KOMF to a field theory. So this is giving a field theory that detects torsion in topological modular forms, and it's coming from starting with S3, looking at its image under this cocycle refinement of the string orientation, and then calculating what the associated invariant of that thing is. All right, so this gives sort of the punchline, a interpretation. Oh, sorry, and I missed an important thing. Who's K? So K here is the choice of string structure on S3, is determined by the choice of string structure. So S3, P1 of S3 is 0 just for degree reasons. P1's in degree 4. S3 doesn't have any cohomology there. So any choice of degree 3 class on S3 is going to give you a string structure. H3 of S3 is Z. So that's my K, is that Z. And then it's taken mod 24 to give you an invariant in TMF. And this gives an interpretation of TMF torsion in terms of field theories. So I want to close by, I don't know if this is exposing you or subjecting you to some physics jargon. So all these structures that I've been talking about have sort of well-known descriptions in the physics literature as well. And I just want to mention what those descriptions are, because I think it indicates at least where this story might be headed in the future. So, this is like some physics that, let me just start with a kind of a blanket statement that usually when you're doing quantum field theory and physics, there are two different approaches. There's a Hamiltonian approach, which in math is related to operator algebras. For example, conformal nets fall into this category, things like that. And then there's a path integral approach, Feynman diagrams, etc. And if you look at any QFT textbook in physics, they're just going to assert that these are the same, that they give the same answers always. Now, in what we've been talking about, the Hamiltonian description is related to this M string orientation of KO. This is the description originally given by Witten in his paper, and he just says in that construction that he's taking this Hamiltonian point of view on understanding that quantum field theory. So the path integral point of view is more related to this map from M string to HMF. And there are various ways of seeing this, but things like supersymmetric localization get thrown in, words like that. But you're trying to do some integral over the double loop space, and you find that it constructs, at least at the physics level of rigor, this type of thing. Okay, so again, usually in physics, they would just say that these are equivalent. But in examining what we've seen up above, they're not equivalent, they're only homotopic. Or rather, maybe better said, the equivalence between them is data, not just property. And that data, that homotopy, is what gives you these torsion variants. So in physics, the homotopy is the same as what's called anomaly cancellation. And this is the data that becomes a torsion variant. So again, there's just a lot of jargon at the moment, but what I'm saying is that there's this translation from this pure math point of view I've been giving about how to start with this mathematical definition of QFT and extract a torsion variant to the physics point of view. And what you find is that this kind of higher structure, in keeping with this workshop, there's some homotopy, and that data is actually very important. That gives you this torsion variant. But furthermore, the story of anomalies in physics is actually more refined than what I've been saying here. There's actually more there that they study. And the hope is that studying that extra stuff is going to give us the torsion, not just from this approximation of TMF, but all of the torsion. So the hope is that a closer inspection of anomaly cancellation will find all the torsion in TMF. So this hope, maybe I should red flag it. This is just my wild optimism speaking right now, but so far there's good evidence that anomaly cancellation is a subtle thing in physics. It's something that's well known in the physics community to be something that's a little bit tricky, a little bit delicate. The TMF torsion has a similar flavor. It's a little bit tricky, a little bit delicate. And at least at this first level approximation, they're matching up precisely. Okay, I think I'll end there. Thanks so much for listening.
Thanks a lot. So, are there questions or comments? Sorry, there's one in the chat. Craig, do you want to post the question yourself? Or
sure. Certainly. Yeah, I was just curious about this last bit where Dan was explaining how there's an assignment of a field theory to a string manifold over M. If you could say something about how one goes about doing that.
Sure. Okay, let me share again. I preemptively quit sharing. Hey, Craig, how's it going?
Hey.
Let's see, did that work? Okay, so there's a homotopy story that you can just kind of read off from up here. And then I'll try and filter it down through the field theory story. So the homotopy story is that given a family of string manifolds, you get a family of spin manifolds. There's a family of Dirac operators associated with that family that gives me something in KO or the base with power series in Q, a family of string manifolds. Similarly, you have this other direction where I'm just going to get some differential forms associated with that family of string manifolds, coefficients and modular forms. Now, the key point is that if you take the Chern character of your family of Dirac operators, it's not going to be equal to the modular form data that you get. The failure will be something related to this theory of mock modular forms, if that's something that you like. And furthermore, the failure will only be like there's an obstruction to making them homotopic. That obstruction is the vanishing of P1 of the manifold, the family of string manifolds in the family sense of P1. And a choice of trivialization will give a choice of homotopy. So that's at least the the homotopy story for what a family of string manifolds does is that, again, there's like an explicit family of Dirac operators, an explicit differential form. The Chern character of the family of Dirac operators is equal to the differential form, but you can choose a homotopy between them if you have a rational string structure. And okay so far?
I think so, yeah.
I mean, I know that Dirac operators may be families of, well, anyway, it's hopefully at least the flavor is okay. So then down here, it's the same type of story. The family of Dirac operators is going to give you a representation of this category of annuli, where, you know, very roughly speaking, it's like you exponentiate the Dirac operator with a time variable in front of it, and that gives you a representation. So it's like e to the t times some operator. That gives you the representation on the upper right corner of the square. And then on the lower left, you're going to get some function that the theory assigns to tori. So that's going to be some function on some moduli space. Very roughly, it's going to be a differential form valued in modular forms. That's a computation to show that that's true. And then again, you can take the trace of your representation of annuli, and you can look at what happens, like compare that to what you're getting on tori. And there's going to be something kind of subtle going on about the moduli of super tori to say that the trace of the family of annuli is not actually equal to a differential form with values in modular forms, but is rather topic to one. And that again is going to be data that's somehow buried in the field theory. So I'm black boxing something, and it's this computation here. But nevertheless, it's sort of the same, like you see exactly the same type of data show up on the field theory side as in that index theoretic description that I gave. And it's about basically pattern matching between those two and doing some computations to get that pattern matching to go. Is that helpful?
Oh, I see. So it's not like, I see. So you're using the construction of these categories as sort of homotopy limits to construct maps between them, rather than sort of a direct kind of, here's a manifold and here's the associated field theory.
Yeah, if you like, it's a generators and relations point of view on field theories that I know, like things that generate some subcategory, the Borsman category, I know what to assign to those. But yeah, it's not, yeah, and in fact, I don't know of that many constructions of field theories that aren't of this flavor. Like the Coe-Borsman hypothesis tells you that this is a great method in general for topological field theories, where there's just one generator. And this is how these things typically go when trying to construct field theories by hand, is that you're just trying to write down generators and relations. Here it's more complicated because it's not a topological theory, so you don't have the Coe-Borsman hypothesis to deploy, but nevertheless, it's the same type of story of like, here's a generating subcategory, here are the values on that, and you have to check compatibilities, and then from there you get your field theory. So here it's sort of identifying the generators and relations homotopically so that you can get this dictionary to go back and forth.
Cool. Thank you.
Yeah.
Any other questions?
I'm not sure if this is a good question, but like, if I may ask, like, you know, you said that the hope is that like to approach the other torsion also in TMF, like for example the two torsion. But
yeah, right.
You were kind of using, as far as I understood, the Bunke and Naumann's theorem, which kind of is mostly about three torsion, as far as I could see.
Yeah, mostly. Yeah.
So you gotta
except for the ZMod 24, which has some.
Yeah, which was like by three. So you gotta prove some two torsion version of that theorem first, or you have to have something like that before you go for.
Well, I mean, we know some things about the image of pi star of M string and TMF, right? I think, but this is
also two torsion. I see.
It's Hopkins and Howald, I think, that it surjects on the connected cover. So
you
know at least that if you're so you know that if you're understanding the invariants that come from M string, that's basically together with like the 24 squared periodicity, that's basically all you need. Right. So the point here is that these specific field theories that came, I agree, from Bunke-Naumann type reasoning, if you refine those theories and you start to see new torsion variants, that at least in principle could be enough to see everything. So these are like one extended theories that you're trying to make two extended, and the hope is that that data and property of two extension encodes these two torsion invariants. I don't have a roadmap for how to prove the full theorem, but that's at least where I would imagine starting, is saying, write down this moduli, like this problem for extending going from one extended to two extended, try to see that again, the data and property of extension is what you need.
And I mean, you just mentioned in that corollary pi3, but I mean, you could have taken any place where that map was injective, and then your method would.
That's right. That's right. The geometry gets harder. Like finding specific string manifolds that map to specific homotopy class, like specific classes, torsion classes, is hard. Partly because we don't completely know M string.
I see.
But yeah, for some of these you have explicit examples, and this this 3-sphere example is one that is the calculations are actually not even that terrible to show these things are true somehow. Well, yeah, lots of classical techniques can be used there.
Right. Great. Thanks.
Sure.
Any other questions, comments?
Well, I want to make a list of what you have black box, namely the Stoll-Steiner technical conditions, so that you can use index theorem for families, Alabismus, and you don't regret not really having a real index theorem for the free loop space on smooth manifolds, right? And also the Bunke-Naumann construction, which also may include something about the differential homology as Bunke understands it as well. And the definitions for the restrictions of the flat metrics to the boundaries of in the objects. And well, I mean, am I forgetting something?
Well, okay.
I mean, I would like to have a complete picture of everything that is needed to understand that be able to write down the details, because I have been following the history from the very beginning, right? So I've seen many versions of it, and all the time it seems it seems it holds water until it collapses always at the same point. And I forgot that also the other thing is that when you to extend that you are at manifolds with corners, right? And your bordings are not written anymore. And Gerd Laures already dealt with that a long time ago. But, so there is many things here that need to be explained. So.
Sure. Yeah.
All these really. I mean, of course, it's impossible to ask that in one hour epsilon talk. You can explain all this, and you did a wonderful job. But it's like to me, the things that were a problem 25 years ago, some of them seem still to be a problem now.
Well, yes, it's true that some of the essential difficulties are still there. I think a few things have happened at least a few things have happened in 25 years.
Oh, yes, sure. I mean, I've been there, right?
Yeah,
so
maybe I could indicate at least what some of those things are.
Yeah.
And how they feature here. So one thing that I didn't emphasize in this talk, but is an important technical aspect to this, is this notion of supersymmetric localization. So what is that? Well, it's basically saying that if I start with something like the loop space or the double loop space or what have you, these things that have S1 or T2 actions, that all of the interesting homotopical data is actually on the fixed points. So, I mean, this result for the free loop space, the history is a bit complicated, but certainly Witten said this in his early studies of the index theorem. Then Bismuth said things along these same lines, where the Bismuth-Chern character is this object that starts with a vector bundle and gives a S1 equivariant differential form on the loop space. And then
but that was there 25 years ago. And the problem was that you could not put a metric on the whole thing that hold water. And that didn't allow you to make the differential, the definition of the families of operators consistent, and you could do it formally. I mean, that's what we all have been doing all the time, like for families and pack families and all. But you could not simply assign an operator on the whole thing.
Right. So my point is that the homotopical data is actually completely contained in the constant maps. So there's a quasi-isomorphism between the S1 equivariant cohomology of the free loop space and just the cohomology of the base space itself. And so in fact, if all you care about are these homotopical invariants, you don't need to study the free loop space, you just need to study the fixed points, which is to say the manifold itself. And implicit in a lot of the definitions I'm making here is that quasi-isomorphism, either proving some version of that quasi-isomorphism or building it into the definition. And again, on the physics side, this is called supersymmetric localization. On the math side, the upshot is that it turns all these really prickly infinite dimensional problems about what is the Dirac operator on the free loop space to a problem in just finite dimensional geometry. And that simplifies these problems tremendously. So that's one thing, one part of this that I didn't get to talk about as much in an hour, but that's one of the insights that I think has happened in the last, I don't know, 10 years or so, as these physicists have become easier to understand, I suppose, is in my opinion, as to why that progress has been made. And so in building these models, a lot of it is replacing some of the older hard infinite dimensional analysis that people were trying to get to work with, I think, easier analysis that's more, I wouldn't call it finite dimensional, but it's parameterized at least by finite dimensional manifolds. And then you can just calculate things using our standard techniques. So that's one ingredient. Another is a lot of the category theory has come a long ways. I mean, manifolds with corners are hard, but you can also work with kind of like a Siegel space style or iterated Siegel space style. So rather than trying to glue things with corners, you're just cutting things in higher codimension. And this sort of point of view from infinity categories and the Coborsum hypothesis has simplified some of those definitions considerably, where these old issues about conformal welding or what have you about 2D field theories, we don't need to worry about that anymore. Yeah, I just think, I mean, some of these things sound rather
sorry, what about the technical assumption that you need to replace the kind of classical ellipticity assumption?
Yeah,
I mean, what is the current status of the Stoll-Steiner extra hypothesis? I'm a bit, I have.
So that extra hypothesis is mine. It's my invention and my fault, if you like.
Oh, I see.
But...
right. That's what I haven't. Well, okay, maybe I'm not enough up to date. So
no. I mean, some of these things are in print and some of these things aren't that I discussed today. And this particular definition is not in print, but I can tell you the flavor of it. Okay. The flavor is that you, again, there's a subcategory of Bordisms that you can restrict to. And the subcategory, you can take like a derivative at the identity, basically, on the subcategory. And that derivative at the identity gives you a family of operators on a a priori Frechet bundle, and then you can Hilbert complete and all this. And you demand that that family have, it's not quite ellipticity, but it's a condition that is sufficient to guarantee the existence of an index bundle in much the same way that index bundle a la Bismuth.
Well, so it seems to the condition that the symbol was invertible, right?
Yeah, that's right. But so the condition that I'm asserting is not that. It's slightly different, and it's different only because it's more flexible. Like, what's the right thing to say? For all of these, it's going to the example to bear in mind is Witten's sequence of twisted Dirac operators. There's no longer one single Dirac operator. There's a whole bunch of them. And things like Fredholmness are not so good because if the index has finite dimensions infinitely many times, it doesn't have a finite dimensional index. So you have to deal with these sorts of things. And so some of the classical notions of ellipticity just don't work, or at least not without refining in some way. So what I'm saying is that there's a version of this that instead it asserts that a certain index bundle construction gives you a smooth index bundle. And it's the one there where, I think I learned it from Bismuth and Fried, where you consider your Dirac Laplacian, you take eigenvalues less than some number, you get a finite dimensional bundle on an open cover, and then they glue to give the K-theory class. So it's exactly that construction. I apologize if this is getting technical.
No, but okay, that's exactly what I was interested in. So that.
Yeah, but I mean, like, some of these things are some of these technical changes, I think, are things that could only maybe have been done in the last 10 or 15 years because of what we know now. And some of them, I think, are just kind of re-examining some of the older ideas in the relationship to index theory that probably could have been done in the 90s, but somehow we weren't looking in this area at that time. So it's a combination of the two. And I mean, I agree with your sentiment that the target has been moving in this area over the years, and it's been frustrating that the target doesn't stay fixed. So somehow, like, people keep moving the goalposts around. I'm not going to name any names for various reasons, but that, I mean, it's somehow what the community is trying to do can be different from time to time. And I'm not attempting to construct a Dirac operator on the free loop space. That's just
no. Well, I'm aware of that.
So in that regard, I think it's still a very interesting problem. I also think it's extremely hard. And so I'm looking elsewhere for solutions here.
Okay,
Anyway,
thank you very much.
Yeah, I'm happy to discuss more. I mean, I can talk about this all day, obviously.
Can I just ask, like, historical question? I mean, like, original conjecture is that TMF should be, I mean, like, TMF as a cohomology theory, at least for some manifolds, should be isomorphic to what these two one-dimensional whatever field theories over M are giving, right? I mean, that should be
yeah, like up to an equivalence relation. Yeah, so that there's I think there are different ways of phrasing it. There's this version in terms of concordance classes, where concordance classes of field theories are isomorphic to cohomology classes. There's a version that's more maybe Siegel style, which is just that there exists a map and it surjects, which is the version that I gave today, where there's just a map on cocycles that surjects. And then there are things in between. I mean, once you have a map that surjects, you know that you can just impose an equivalence relation, which is that two things are equivalent if their image is the same. So for me, the existence of the cocycle map that surjects is the first and more important one. And then whether or not that equivalence relation is concordance is an interesting, but in my mind, secondary question.
And I mean, do I understand this correctly? Before you, I mean, now you of course have like lots of classes in TMF, which you sort of interpret in terms of that field theory stuff. But before, the thing that was known is just like what happens on the point, and how much did these guys knew? I mean, Stefan.
Yeah. So right. And well, okay. I think they know a lot. And what they've written down is a subset of that. So I can either comment on the things that they've written down, or I can comment on the things that I think they know, which I might misrepresent. So I'm a little hesitant. But nevertheless, I think that they've known basically where integrality and modularity have come from for a while. So that integrality of field theories comes from the fact that the Hilbert space of the theory is a vector space.
Yeah.
And so things like integers exist there, like as dimensions. So that's the integrality. The modularity comes from the fact that there's compatibility with those integers with values on tori, and there's this SL2Z action on the moduli of tori. And that's very much in keeping with what I described today, that the integrality comes from these annuli and vector spaces and yada yada, and the modularity comes from tori. I think the new thing here is that when you think about these as being homotopy compatible rather than just compatible, you start to see torsion as well. And that's I think, if you want to put this in historical perspective, that's probably the only new thing that I'm saying today, is the homotopy compatibility gives you torsion classes.
I see. Cool. Yeah, no, great. Thanks. That sounds like very nice. Good progress.
It was fun. It's been really fun. I mean, I don't know. I think this is an area that, for a variety of reasons, is sparsely populated these days. But I hope that more people work on it, because I think it's fascinating stuff, and I think that we could use friends over here. You know, it's hard work and it's fun work, but it's hard work, and it's good to have collaborators. So yeah, I mean, I've been doing things in collaboration as well, and it's been fun to.
I just remember attending a summer school as an undergrad. Actually as a master's student in 2009 in Max Planck about this stuff. You know, these guys talking.
I think I was there. Yeah. Yeah. And I think, I mean, to their credit, I mean, they've had tremendous impact on me and on the field, and I think that what they know is only a fraction of what's been written down. And when you get to have conversations with them, you can learn so much from. I mean, they've thought about this problem for, I don't know, like 20, 25 years. It's incredible the depth of knowledge that they have. I also think that it tells you a little bit about how hard the problem is. If the two really smart guys think about it for 25 years and haven't solved it, it's probably difficult. So I think part of what, you know, anyway, I think it's a really exciting area. I think that we're just on the cusp of being able to understand a lot more. Part of it is the new technology that we have from higher category theory and just better understanding of TMF from Jacob Lurie. But I also think that it's a problem that will probably be solved if the community gets bigger. I think we need more people working on it. And so, you know, if you have good students.
Yeah.
Anyway.
No, I just remember like getting really lost in the other side of the story somehow, whenever it came to some kind of very decorated field theories with lots of decorations there. And then eventually it ended up going into some topological vector spaces or something like this. And that's, I remember where I was.
This is true.
Really,
yeah, the functional
really
analysis
lost,
is real.
They tried many things.
Yeah.
I mean, it was in the 2003 one, then it was von Neumann algebras decorated with, I can't remember what.
Yeah.
I mean, that,
this remains a problem. This remains a problem.
Yeah.
I think one thing I might mention is that the examples that come out of this point of view I'm advocating today, what's the right way to say this? Geometry doesn't like completions usually. Things like the bismuth superconnection make sense on smooth spinners, but the minute you L2 complete, it's no longer going to be continuous. So like a lot of the earlier stuff that involves completions, C-star algebras, von Neumann algebras, et cetera, it's probably not going to be quite the right object to work with when you're doing these smooth geometric operations. So again, I mean, this is something that I've only really come to appreciate in probably the last 6 months, but these are the types of insights that we're learning where it's okay, you have to start with probably similar ideas to what they had in 2004 about, you know, hyperfinite type 3-1 factors, many decorations of analytical things, but you need to somehow find a way of making that into something that plays more nicely with smooth geometry, with smooth manifolds. And I can imagine many ways in which to do that. It's not clear that it's even going to be a unique problem, but that's the type of new thing that I think needs to be done. Thank you for all the questions. This is great. It's fun to talk.
Cool. Thanks for
the
thanks for the nice talk. I was having fun. It was nice.
Oh, great. Well, that makes my day. Thank you.
I think you should have applause for answering the questions.
Thank you a lot for the talk and well, for being with us from so far away.
Hands again, just to keep the forms.
Yeah, and thank you for organizing this. I mean, it's great to see everybody. It's great to hear some interesting talks. And
well, we don't see everybody because of this time zones thing, right? I mean that.
Sure.
But it's what we can do.
Yeah, right. I mean, right. We have to make the most right now. So here we are. This is still better than sitting alone in my basement doing math. So, you know.
I stop the recording now. It doesn't mean that you have to go, but I stop the recording.
Yeah,
Okay.
no, I think that.